Hello everyone. Today we will see about one topic from Antennas and Microengineering, unit number 3, antenna arrays and applications. This is the syllabus. And antenna arrays. Several antennas are similar type of arranged in a system to radiate more in a desired direction with a high gain. So, in order to increase the directivity and all antenna characteristics, we are going to combine a number of antennas. Similar type of antennas we are going to group here. This can be achieved by combining individual antennas radiation in a desired direction and cancelling radiation in undesired direction. That system is called as an antenna array. And antenna array is a system of similar antennas oriented in a similarity to get a greater directivity in a desired direction. An antenna array is said to be a linear if the elements or antennas are equally spaced along the straight line. That means the antennas are placed in a straight line with the equal distance. The linear antennas are said to be uniform linear array if all the antennas are fed with the current of equal magnitude with a progressive uniform phase shift along the line. Various forms of antennas are array antennas, right? Practically various type of antennas are available. Some of the important one is broadside array, end-fire array, and collinear array, and parasitic array. And array of 2-point source. This is a basic antenna, very basic antenna. When you are going to discuss about antennas, we will discuss about this antenna array of 2-point sources. We are going to consider only 2-point source, and we are going to find out the radiation pattern for a 2-point source. And point source nothing but an isotropic radiator occupying a zero volume. A number of similar point sources are arranged in the form of array. The simplest condition is number of point sources will be an array will be 2. And the 2-point source, the array of 2-point source can be understood in 3 different ways. One is the 2-point source with equal magnitude and equal phase, and 2-point source with the currents of equal magnitude and opposite phase, and 2-point source with the currents of unequal magnitude or in a phase. Here we will see about the 2-point source with currents of equal magnitude and equal amplitude. And we can consider the diagram, right? Here we have 2 points A1 and A2 are the point source, and the 2 point source will be excited by a signal having equal magnitude and equal phase. That the separation distance between the two antenna will be at D, and at distance point P we are going to measure the radiation pattern, and the distance between point source A1 and P is R1, and A2 and point source P is R2. And if we are going to form a triangle, means we can find the value of A1 LM, the length of LM will be D cos phi. For a long distance, R1 and R2 is equal to R. For approximately R1 is equal to R2 is equal to R. We can consider. And the path difference is given as D cos phi, and in terms of LM, the path difference is D cos pi divided by lambda, and phase angle psi is equal to pi into path difference, and phase angle psi is equal to pi into D cos phi divided by lambda, and psi is equal to beta cos phi divided into radian. And where E1 is the far field at distance point P, and E value of E1 is equal to E0 due to Bragg psi E2, and E2 is the far field distance far field at point P due to point source A2, and E2 is E0 by Ez by 2, and E0 is the amplitude of the both field components, and we can write the value. The field at any point is given by E2 is equal to E1 plus E2 is equal to E0 into E to the power psi by 2 plus E0 into E to the power psi by 2, and we can take E0 as a common term, and we can write this value as cos by psi by 2, and you know the value of psi, substitute the value of psi here. 2Et is equal to E0 as cos beta d cos theta cos phi by 2, and we can write the array factor. Array factor is Et by E max, and the field is given as maximum field is given as E0 E max is equal to E0, where array factor Et is equal to E0 is equal to cos beta by cos phi divided by 2. And for field pattern we need to calculate the maximum, minimum, and half orbit directions. And for maximum direction the amplitude value will be 1, so we can write in terms of E is equal to cos pi beta d cos pi by 2, and D is equal to lambda by 2, and beta is equal to 2 pi by lambda, and we can substitute the values here, and we can consider the common term, and we can write E value as cos pi by 2 cos pi. And maximum direction, in this direction we have a maximum value will be plus or minus 1. So we can write E is equal to plus or minus 1, and general terms we can write in terms of plus or minus n pi. We can substitute the value of 0, 1, 2 for n value. If n is equal to 0, we have a cos theta value as 0, which is theta max is equal to 90 or 270, and if it is minimum, the value will be 0 in terms of pi. General equation 2n plus or minus 2n plus 1 by 2, and we can substitute the value n is equal to 0, the cos minimum is equal to plus or minus 1, which is 0 and 180 degree. For half power beam the value will be 1 by root 2, and half power point the direction will be field is 1 by root 2, and we can write the value is equal to plus or minus 1 by root 2, and E is equal to plus or minus 1 by root 2 means general term plus or minus 2n plus 1 into pi by 4, and we can write the value as half power beam d half power for directivity, half power per direction, Hopper point direction, HPPD is equal to 1 plus or minus 1 by 2, and we can write HPPD is equal to cos minus 1 plus or minus 1 by 2, which is 60 or 120, and this is the final radiation pattern. The maximum direction will be 90 to 70, minimum direction will be 0, 180, and Hopper direction 60, 120, and this is the radiation pattern for a array of point source with array of 2 point source with the excited with the equal magnitude, equal phase. This belongs to case 1, and this may be asked for 13 mark question. Thank you.